Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now. Today we're diving into something so fundamental that without it, you wouldn't be sitting in your chair right now. You'd be flying through space at the speed of light.
That's like an upgrade, right?
Yeah.
But that's right. Today's episode is all about mass. What is it? Where does it come from? And more importantly, why do physicists always make things more complicated than they need to be?
And if you realize we've been trying to do like a series of episodes on mass here. So like from what is the Higgs boson to why we don't get all of our mass from the Higgs bosons, and finally we've come to like what is mass exactly, because we're still unclear about why it is so complicated.
Yup. And we're talking about different things, and coming back to why physicists always make things more complicated than they need to be. Well, it's our job right now. Like we're making it less complicated for you all, right? Right?
Yeah, but seriously, mass is one of those things that we all think we understand until we start asking the tough questions. Like, what is rest mass?
Well, rest mass is the thing that only exists because Einstein came along and said, "Hey, what if I told you there's another kind of mass?"
Yeah, and he could have said, what if mass was just energy in disguise?
Exactly. So let's break this thing down. So when we talk about rest mass, we're talking about how much energy an object has when it's just chilling. Like it's a chill guy.
Yeah, chill guy.
So it's not moving, it's not accelerating, just existing. Just existing.
That's the whole point of Einstein's famous equation, E is equal to mc squared. It's not saying total energy is mass times the speed of light squared.
Yeah, exactly.
It's saying that rest energy, the energy of something just being there.
Just being a chill guy.
Yeah, just being a chill guy is mass times the speed of light squared.
Rest mass times the speed of light squared. Yeah.
Correct.
So the way we measure mass is classic physics trick, you can say, is apply a force, see how fast it accelerates, and do some division. F equal to ma, another very, very famous equation.
Correct.
So the heavier something is, the less it accelerates for a given force, and if you put more force, then you'll have to, then it accelerates more.
Yeah, which is why pushing a shopping cart feels different from pushing a fridge. Unless you're in a supermarket with one of those rogue carts that basically refuses to move straight.
Oh yeah, the wheel is like broken off and...
Yeah, no, one wheel doesn't turn only sometimes. It happens. Then you basically discovered a new form of physics.
And when you said fridge, I remembered us talking about pushing up the fridge up a hill loaded with TNT in one of our previous episodes. I won't name it, but...
Yeah,
I think
the slingshot ones.
Yes.
We're not going to reveal it for you.
You'll have to listen to all of them to find
Just
out.
take a hint.
The hint is it's one of the recent episodes. Okay, fine. So those shopping carts you were saying, I think they operate on chaos theory, bro. Like those shopping carts, the wheels.
Yeah.
I think they operate on chaos theory. They're like that erratic, you can say. But okay, fine. We know what mass is in a practical sense. The bigger question is, where does it come from? And this is where things get even more weird.
Enter the Higgs mechanism, aka the reason why particles have mass in the first place.
Some particles, not all. So that's another caveat, right? So learn, like, if you want the exact thing, then we have another episode on what is the Higgs boson. So the Higgs, but we'll give a summary.
The Higgs field is basically like this invisible energy field that fits all of space. Same thing, no. Particles interact with it, and depending on how strongly they interact, they gain some kind of mass. Kind of like how people wading through water move slower than...
Wading through water.
Okay. They move slower than people walking on dry land.
Except in this case, the water is everywhere, and if it wasn't, the electron wouldn't have any mass, and atoms wouldn't exist, and poof, no universe, no me, no you, nothing, okay?
So basically the Higgs field, and if the Higgs field didn't exist, we'd all be moving at the speed of light.
If we would have existed, yeah, but if it doesn't exist, then we also don't exist, so fair enough.
It sounds cool, very cool in theory, unless you realize that means no more atoms, no more planets, and no more quark talk.
Wait. No more quark talk. That's such a... Like, the universe wouldn't be the same without it, okay?
Exactly, and you know the wildest part? Before the Higgs mechanism was introduced, physicists like the great Steven Weinberg tried to build a theory of weak interactions without it. But the problem was his equations predicted that the electron had to be massless.
Well, spoiler alert, he learned from quark talk that it's not.
Right, and the reason massless particles always move at the speed of light is straight from Einstein. If you have zero mass, you have to travel at the speed of light, and vice versa. If you're moving at the speed of light, your mass must be zero.
I mean, there are some exceptions to that as well, but we won't be talking about that right now. So the next time you're running late, you can just tell people you're trying to achieve masslessness so you can move at light speed.
Yeah. So now that we've laid the groundwork, rest mass, energy, the Higgs field, we still have a lot to uncover.
Speaking of photons, here's where things get even wilder. So if you're moving at the speed of light, there's actually a unique answer to the question, what is your rotation in the direction you're moving?
And by rotation, we're talking about spin, not the kind that you do in a swivel chair, but the quantum property that particles have.
Like, not like a ballerina, we're talking about a quantum spin. We're not talking about a spin, okay?
It's different.
Yes. We spoke about in our...
first episode.
Yeah, in the standard particle of physics, right? So, if you're a massless particle like a photon, everyone agrees on your spin direction. But if you have a mass and you're moving slower than light, which is literally everything other than a photon right now, then things get messy. Because different observers will see your motion differently. One person's forward is another person's backward, right? Everything is relative.
Yeah, which is why Weinberg's original theory ran into trouble. His equations needed a well-defined answer to his rotation question. But that only works if the particle is moving exactly at the speed of light, which only happens if the particle has zero mass.
But thankfully, the Higgs boson comes to the rescue. Oh, we're talking about Higgs bosons a lot recently, huh? So it fills space like an invisible field, and when particles interact with this field, they slow down, kind of like running through water, as you said, and that's what gives them mass. That's fine. But by breaking that original symmetry in Weinberg's theory, Higgs makes sure that particles move slower than light, letting the real world match up with the equations and letting everything else exist and not letting everything move at the speed of light and crashing into each other and dying.
Thank you for that great monologue. But here's the twist about it. We keep talking about mass as if it's a built-in fundamental property, but modern physics sees it slightly differently. Mass is really just a measure of how much energy something has when it's sitting still.
Which makes sense, right? Energy comes in different forms: kinetic energy, potential energy, gravitational energy, mechanical energy, etc. And what we call mass energy. So when you accelerate an object, you're just converting one form of energy to another.
Right. The heavier an object is, the more energy it already has in the form of mass. So to get it moving, you have to add even more energy, which means more work. That's why heavier objects are harder to accelerate.
And that brings us to something called relativistic mass.
Ah, yes. The thing that confuses everyone the first time they hear about it.
Yup, including me, kind of.
Same. The idea here is that as something moves faster, it acts as if it has more mass. Not because its actual rest mass is changing, but because its total energy is increasing, and energy and mass are two sides of basically the same coin.
So earlier I had said, right, that there was an exception to the vice versa part of thing, what you said, right? Like if you are a photon, you're massless, you move at the speed of light. But vice versa, if you move at the speed of light, you're massless. That's like the exception I'm going to be telling right now is if you're going near the speed of light, let's say you're running right now, okay? Usain Bolt is running, okay?
Okay.
He's running and he's like slowly increasing his speed, and as he gets closer to the speed of light, his energy increases obviously, like because he's running faster, but his mass also increases, and that makes it harder to accelerate even more. And it's like running with Usain Bolt, and he is wearing a backpack that gets heavier and heavier with a black hole inside it that gets heavier, and it gets heavier the faster you go.
Basically, what Arnav is trying to say is that the rate at which his mass increases, which is determined by something called the gamma factor, is much, much more than the rate at which any object in this universe can accelerate.
Exactly.
So you can't accelerate to the speed of light.
which is why you can never actually reach light speed, because the amount of energy required would also become infinite, or the time required would be infinite. So something's infinite, so you have to give up.
Tough luck for all the sci-fi spaceships trying to break that barrier.
Yeah, unless you've got interstellar time space swap drives lying around.
No, but I actually read it somewhere that if you warp space-time in a certain kind of pattern or something, you can theoretically go faster than the speed of light, but
You have to warp the fabric of space-time itself for that.
which takes a lot of mass concentrated in a really small space.
Black hole.
Yeah, we'll talk about that later though.
Yeah, but don't lose hope just yet. I know I said give up, but don't lose hope just yet, because we'll also talk about whether Mars is even real, or as real as we think it is. So you can lose hope after we talk about that.
Alright. So now we've talked about Mars, energy, and why you can't hit light speed unless you're a photon with places to be. But there's one term that gets thrown around a lot, and honestly, it probably shouldn't.
Yes, relativistic mass. If there's one thing we could erase from physics textbooks with a single click, it'll be this, because it's kind of... Let you just say.
Okay. That was a bold statement though. Almost as bold as me trying to explain relativity without getting a headache.
Einstein himself probably wouldn't mind if he banned the term, because the problem is this. Mass in the proper Einsteinian sense is how much energy an object has when it's at rest. The number doesn't change no matter how fast you're going, because that's a constant, unless you change the mass of the body. But in the so-called bad old days, long ago, people started calling the total energy of a moving object its relativistic mass, and that makes it sound like the mass itself is changing. The rest mass itself is changing, which is misleading.
Exactly. Instead of saying your mass increases as you speed up, the better way to think about it is your energy increases as you speed up.
Yeah, exactly.
The math still works the same way, but conceptually it's much cleaner. So in conclusion, let's all collectively forget the term relativistic mass and call it what it is. Just energy.
Agreed. So while we're on the topic of mass, there's actually another way to define it, and this one is actually useful. It's not relativistic mass, it's gravitational mass.
Which sounds fancy, but is basically just how much gravity does an object create.
So basically, more mass, more gravity. Simple as that. Linear relationship. That's it. So when Newton was doing his thing, writing physics laws, getting hit by apples, ruining students' lives, he defined mass as force divided by acceleration. F equal to ma, whatever. A is equal to F by m. That's now what we call inertial mass, which is how hard it is to push something.
But there's another question you can ask. How much gravity does an object cause? Or put another way, how much does it respond to gravity? That's what we call gravitational mass.
And in principle, these two things could have been totally unrelated, right? What you might think initially. Just like electric charge determines how much a particle responds to an electric field, you could imagine that gravitational mass would be some separate property from inertial mass.
But here's the weird part. It turns out that they're the same. That's the beauty of what we call fields.
Yeah, it's one of those why is the universe like this questions, but in a nice way. Newton just kind of noticed that the mass that determines how an object accelerates is exactly the same as the mass that determines how much gravity it generates.
Which is why all objects fall at the same rate in a gravitational field. If you ignore air resistance, a feather and a bowling ball hit the ground at the same time.
Which is a beautiful
YouTube video.
Beautiful, you should watch it. Just go check it, yeah.
Yeah, check it out.
There are multiple of them, there's not one, but just watch it. So this equivalence between inertial and gravitational mass is so fundamental that Einstein built the entire general relativity on it. But at that time, Newton didn't really have an explanation because he was before Einstein. It was all just a fact about the universe.
A lucky accident for physics and for Newton's reputation.
Yeah, imagine if it wasn't true and he had to rewrite all of classical mechanics.
That would have been massively unfortunate.
You mean massively? That's what you meant to say?
No, sure. Alright. So we've covered mass, the Higgs boson, and why Newton got lucky now. But now we're stepping into the deep end. So why are gravitational mass and inertial mass the same?
Well, as we said, even Einstein didn't fully get it at first. He came up with E is equal to mc square in special relativity, but then spent 10 years figuring out general relativity. And then after he did all that, then the answer actually became obvious, as we said. And it does take a whole new way of thinking about the universe to see it, right?
Exactly. General relativity tells us that gravity isn't just some invisible force. It's actually the curvature of space-time itself. and that curvature depends on energy, not just mass.
So instead of two separate properties, one for inertia and one for gravity, they both basically boil down to the same thing, which, like, you might have guessed it, energy.
Yeah, and that means that if you've got mass, you've got to resist being pushed and you're going to bend space-time. The same number describes both effects.
Yeah, it's an and, not an or.
Yes.
But there's an interesting twist here. Motion matters. Imagine you've got a barbell, okay, like a dumbbell, floating in space. And let's say it's the mass of the sun. It's a barbell, the mass of a sun. It's floating in space. So if it's just sitting there, it obviously does create a certain gravitational field. But that would be the gravitational field, like the same. So now it won't be the same gravitational field as the sun because the shape is different. But you get the idea, right?
Yeah.
But if it's spinning, suddenly its gravitational field changes. And it depends on which direction it spins and how it spins and how fast it spins.
Yeah, all Stephen Hawking stuff. But because it spins, it has more energy. Because it has this stuff called rotational energy as well, rotational kinetic energy.
Yeah.
And in relativity, energy bends space-time, not just mass.
So in theory, the Earth's gravitational field is actually slightly stronger than it would be if the Earth wasn't spinning. I mean, a different thing, if it wasn't spinning, we wouldn't be alive and all. That's another thing. But its gravity would be slightly lesser.
Yeah, but the effect is also insanely tiny. So small that there's no way to measure it on Earth as well.
Yeah, it's not rotating that fast also. Like just 1200, I think. 1200 kilometers per hour. I don't know.
Yeah, but to get an effect that is actually measurable, you need to go like close to the speed of light.
Exactly. So if you take then something that's really extreme, okay, because you want to measure it, right?
Yeah.
So if you take like a rapidly spinning neutron star or a black hole, then you get the effect as like a measurable outcome.
Exactly. In fact, spinning black holes actually drag space-time around with them. It's called frame dragging.
So basically real life lag, kind of.
Yeah.
So that's kind of also the closest thing to real life time travel we're gonna get, right? Because time itself is warped and space itself is like all bonkers.
Space-time is one thing, okay?
Yeah, I know.
For now, give physicists another 200 years and then who knows what might happen.
Yep, maybe even 100 years, who knows? Alright, then let's take this even further. What happens if you have a lot of mass in one space?
Basically get a black hole.
Exactly, we spoke about this like in so many episodes. But yeah, I think we can like, black holes are common knowledge. So to wrap it all up, mass isn't just some mysterious chunk of stuff sitting in space. It's really a measure of how much energy something has when it's sitting still. And thanks to old Einstein over here, old Albie, we know that energy and mass are two sides of the same coin.
And if you throw general relativity into the mix, you realize that mass isn't just resisting motion, it's bending space-time itself. That's why gravitational mass and inertial mass are the same thing.
So if you're also feeling weighed down, it's not just physics, it might also be your life choices.
Or just too many burgers.
Yeah, McDonald's on top, bro. Either way, we hope this episode made mass a little less confusing, or at the very least, like, made you feel a bit smarter for the next time someone like invites you to Einstein's party.
Sure. And if someone does, you need to invite us to that party.
Yeah, our email is quarktalkofficial@gmail.com, okay?
Yeah, we'll catch you next time. Until then, please keep your minds relatively open.
Bro, that was such a bad dad joke.